All right, I guess I'll get started. So I'm Jonathan.Helmus, and I'm working at the UConn Health Center, but a lot of this work was done at Ohio State University. And I'd just like to start my talk by thanking the organizers of this conference for inviting me and letting me present my work on nmrglue. So nmrglue is an open source Python module for working with NMR data. It kind of has a two-prong approach. It wants to tie together existing NMR software packages and also provide an environment for the rapid development of new processing methods and analysis routines and visualization. So in this talk, I'm going to give a little short background on NMR and protein NMR, discuss a little bit about why I wrote nmrglue and some of its design and features, give you some examples, and then since most of you are probably never going to run NMR, some opportunities for code reuse that you might want to use from nmrglue. So nuclear magnetic resonance, or NMR spectroscopy, is an analytical technique that is used to characterize the structure and dynamics of chemicals. The most common use is for small organic molecules. This is the kind of NMR you might have seen if you took an organic chemistry class. But NMR can also be used to identify larger molecules such as proteins. So if we look in the protein data bank, which is just a big database of all the known structures, about 10% of them have been solved by NMR, and that accounts for about 8,000 structures. And that number has been growing over the years. So how does NMR work? First, we prepare a sample. We have to include isotopically labels. These are really small samples, so in the solution NMR, we're talking about less than a milliliter of solution in that little sample tube. In the solid state, we pack them in tiny little rotors. We're talking about a few milligrams a sample. We put the sample in a large magnetic field. This is created by a superconducting electromagnetic, and they're quite large, very expensive instruments. We apply a series of very precisely timed radio frequency pulses, and then we collect the time domain's response to this. We have to do some kind of signal processing to take this time domain data into the frequency domain, and then we can visualize, analyze our peaks, extract any parameters that we might want. So if we have a small molecule, we get a very simple spectrum, just a few number of peaks. But if we could do something like a protein, we're going to get a lot more peaks. So this is ubiquitin, which is just a long string of 76 amino acids. If we were to count the number of hydrogens, there's about 615 hydrogens, which means we should have about 650 peaks in that spectrum. The obvious problem here is we can't resolve individual peaks. And this is one of the key challenges in protein NMR. How do we gain additional resolution so that we can see individual peaks so that we can extract parameters? One method is to move to an additional dimension. So these are two-dimensional spectra of another small protein. This is GB3, which is 56 amino acids. And you can see just in 2 dimensions, we have enough resolution that we can basically detect individual spin pairs and assign them to different nuclei in the protein. Now, 2 dimensions, if we go to larger proteins, we need additional resolution, so we move to 3 and even 4-dimensional data sets. So all of these experiments are pretty standardized now. The problem is, as we move to larger dimensionality data, our file size gets much larger. So a 3-dimensional data set can often be 1 to 2 gigabytes in size. 4-dimensional data sets are even larger. And so we need some kind of software to deal with this. One thing that I really found exciting about NMR as I was entering my graduate work was that there's ample opportunities for programmers. So in the collection and the processing and in the visualization and assignment and in the analysis of NMR spectra, all of these have lots of interesting programming opportunities, and they include a lot of complex mathematical fields. Since there's so many opportunities, it also means that there's lots of groups that like to write software for it. So I just kind of pointed out on the bottom here some of the software packages that are used quite often. And as you can see, most often, a lot of these aren't shared between the different steps. So it's not unusual for you to collect your data with one piece of software, process it with another, and then visualize it with a third, and even analyze it with a fourth. So with all this software out there, you might say, why write more NMR software? It seems like there's plenty. So some thoughts that I had is, first of all these software packages use different file formats. There's no standardized version of some, let's all put our NMR data in this format. So that means we need some way to interconvert between all these different formats. In addition, NMR is an active research field. There's constantly being new experiments and new methods being proposed in the literature. So we need software that can deal with these new experiments. So really, we need some kind of software that gives us a scripting or a macro language. And there are very few of those out right now, and only one that uses a standard programming language. Also, protein NMR by its nature is very repetitive. We have spectra with hundreds or thousands of peaks that we need to analyze. So we need some kind of software that can be automated. The existing software available doesn't really do this very well. And finally, very few of the packages are open source. So even though we use very standard processing techniques and algorithms, oftentimes you have to recreate your own because nobody's written one that you can go and look at the source. So with those in mind, what did I want to design NMR Glue for? So NMR Glue aims to be a powerful yet easy to install and use package. So for this, I chose Python, and in conjunction with the NumPy and SciPy packages, it really offers you a very powerful and easy and clear syntax to attack scientific problems. Installation is very easy, even for scientists. You can, if it's not already on your computer, you can just download a nice installer. And one of my favorite things is there's lots of documentation and lots of tutorials on these, and I don't have to write them. So I can point, some new undergraduate in our lab to that, and he can get up to speed without me having to do a lot of work. So NMR Glue also aims to be a system for interconverting between existing NMR programs, since there's so many of them out there. I tried to be very careful not to create a new standard. We have all these. We don't want to make another one so that there's just one more. So to do that, all the existing files are read directly from NMR Glue, and NMR data is stored as a NumPy array. Spectral parameters are stored in a Python dictionary. I also wanted to be an environment to rapidly develop new processing and analysis and visualization methods. So for this, NMR Glue contains all your standard NMR processing and analysis routines. You can build new ones from the large collection of routines in NumPy or SciPy or whatever your favorite Python module is. And also, IPython, as I think we all saw this morning, is a very robust environment for visualizing data. And you can even do this for NMR once your data is in a palatable format. So just a short overview of what's included in NMR Glue. So we have a bunch of modules for reading and writing different file formats. We support both Bruker and Agilent and Variant, which are the two large spectrometer companies, and then NMR Pipe, the Roland NMR Toolkit, and Sparky. We also include a module that can convert between any of these formats. And all of these submodules contain routines for so-called on-demand or low memory reading of the files. I'll go into that a little later, what exactly I mean by that. We also include processing functions, so you have your common NMR functions, you have some baseline linear prediction, and then also I include functions that look a lot like the most common processing software package, NMR Pipe. We include some analysis functions, so you can do peak picking and some line shape fitting and simulation. So with that, I'd like to give some examples of how I've used NMR Glue and how I can envision other people. So the first one is just reading data, modifying it slightly. So we can write from a number of different formats. This example is reading an NMR pipe file. So the syntax is really easy. You just import the package. We use a read function. Whichever format you happen to be using, you can use that submodules function. Normally, you just have to pass the file name. For some of the formats, it's a little more complicated, so you have to pass a couple of keyword arguments. We can examine the data. We see this is two-dimensional data. We can see the shape. It's complex. Most NMR data is complex, if not hyper-complex. We can look at some of the parameters that are stored in the dictionary. We can also examine the data. This is one of the few packages in NMR where you can actually look at the raw numerical data. If we want, we can modify that data, so we can set the first indirect dimension to all zeros. Anytime we change the data, that's just happening in the NumPy array, so it's just in memory. But if we want a copy of that, we can save it. All of our submodules also allow writing to that format. We can also convert the syntax for this. We read in the file. We initiate a conversion object. And then we load data into it with a from function. Then we can write out to it or create new data with a to. And then we can save that data. And that's a perfectly valid, in this case, Sparky file. With our data in a NumPy array, we can also do a lot of interesting processing techniques. So nmrglue contains a standard processing functions, but we can also develop new ones. So a few years ago, Raphael Buchweiler suggested that a simple covariance calculation can be performed on NMR data, and it can actually give high-resolution data for a certain subset of classes of experiments. But none of the standard processing methods support a covariance matrix because no one had suggested using it before, even though it's a very simple mathematical operation. But if we have our data as a NumPy array, it's very simple. So in this case, we just open our data. We can compute the covariance. And then if we want, we can plot it or we'll do whatever we want with our data. This changes a little bit. So this lab actually came up with an entire MATLAB package just to do covariance processing, even though in nmrglue it's one line of code. So we can make some more complicated plots. So these are very nice if you want to put them in a paper. I really like them because when my advisor comes and says, I don't like blue, I want them in red, I can go and edit my script and change a color and not have to redo everything by hand. In this plot, we're adding these little strips so that readers can get some information on our signal noise. To do this, we can make a unit conversion object so that we can index our arrays by some more natural units that we see in NMR. So the strip plots here are just generated. So we're going to take them at 105 ppm and 115. So these are just units that we use in NMR. We can also do some analysis. So this is actually the original problem that eventually led me down the rabbit hole to write nmrglue. So we had collected some relaxation data. So we just had a series of two-dimensional spectrum. And we wanted to see the peaks, and they should decay over time. We already had all the data. And we said, well, we'll just look at the heights of each of the peaks and watch them decay. Well, it turns out the peaks would shift a little in between spectra. And so my advisor said, well, just take a little rectangular box around the data and do simple summation and do that. Well, I looked around and I said, I have no idea how to do that. None of the software packages let you define, give you access to the raw numerical data. So I said, well, I'll just write my own. And but if you can get your data in a NumPy array, all you have to do is do a little slicing. So this script is really just all boilerplate to load in our box limits and our spectras and everything. But the real meat of the thing is this simple slicing array, or we just slice the array, take a summation, and store it as a trajectory. With it in a NumPy, the trajectory is also in a NumPy array, so we can fit them using whatever our favorite optimization scheme. We can visualize them, things like that. So I also want to give some examples of why you might want to use some code from nmrglue. I know most of the people in the audience probably are never going to run an NMR spectrum, never going to look at one, but I think there's some routines in nmrglue which might be of interest to the wider scientific community. So this is these on-demand or low memory file access. There's a constrained multivariate least squares optimization, and some n-dimensional peak picking and n-dimensional line shape fitting. So all this code is available at GitHub under the BSD license. So to start out, I think it's a very common problem in science that we find some big data set in some file format that we didn't decide upon. We're just stuck with it. And we want to read just a small segment of that data set. So maybe this is multiple gigabytes or something, but we can't just memwrap the file because it doesn't have some nice contiguous structure. So what we need is some way of just reading a small portion. So this same problem occurs in NMR data. So NMR glue offers a data ND object, which looks and acts to the user a lot like a NumPy ND array. But your data is only read from disk and into memory when you request a slice. So anytime you do a slicing operation, you get back an ND array object. And most slicing methods are supporting. You can use ellipses. You can use start, stop, or start, end, and steps. Your steps can be negative, things like that. You also have your standard attributes. You can look at the dimensionality, the shape, the D-type. You can also iterate over these. They do what you expect. They iterate over the leading axis. If you want to iterate over something else, you can do a swap axis and transpose methods. These just return a copy of the object with the new axes ordering. The nice thing is this object is really easy to adapt. So you just have to define 3 methods: initialization, a copy item, and then this fget item. Which fget item is basically just a patch of get item, that you're guaranteed will be passed a nice tuple of slice objects. So if you have 3-dimensional data, you're always going to get a 3 tuple. And all your slice objects are going to have you're guaranteed to have a start, an end, and a positive step size. So you just have to figure out how to read the data from the file and get back an array. Everything else is taken care of. So the example, we can read a 3-dimensional NMR pipe file. We can look at its shape. We can, as soon as we actually request a slice, we can look at the data. We can request some larger ones, and we can transpose the data and get everything we kind of would expect. NMR glue also gives a bounded least squares optimization. So there's been some discussion on the SciPy mailing list that people would like something like this, that we can do least squares optimization but put constraints on the variables. There are some options. There's some packages that do this: LMFit, MPFit. There's a pull request right now. But all of these kind of have a more complicated call structure. And I wanted a version that I could just drop in replace for SciPy's least squares. So least squares bound, the call and return are identical to SciPy's least squares. Except you also have a bound parameter that you can either be none, in which case no bounds are included, or you can have a tuple of a min and a max. Either of those can also be none. The restraints are imposed by a variable substitution with some signs and square roots that have natural limits. And this package is actually, I pulled it out of NMR glue because I know there was some interest in it. NMR glue also gives you n-dimensional peak picking. So you can pick data or pick peaks in 1-dimensional, 2-dimensional. There's a number of different algorithms. You can estimate some line shape parameters. You also can do line shape fitting once you fit once you've picked your line shape. So you can do any dimensional line shape fitting. You can simulate these peaks. You can use some built-in line shapes. You can also define your own. So if you want additional information, NMR glue is hosted at Google Code. The actual source code is on GitHub. There's a tutorial, a reference guide, more examples. And with that, I'd like to just end with some acknowledgments. So this work really, I'd like to thank my PhD advisor, Chris Jaroniak, for letting me do this work, kind of a skunkworks project. And then my current postdoc advisor at UConn, Jeff Hauk. And with that, I'll take any questions, and I'd like to thank you for your attention. Oh, it's all automated. You tell it a threshold or a minimum separation, something, and it goes and segments the spectrum, finds peaks, things like that. Yeah.
So do you have any kind of sample workflows up, especially for things like 2D NMR data?
So the tutorial does. It is not going to show. There is some sample data that you can play around with, but it doesn't go through a processing. I've been kind of meaning to do it, but the real problem is I'm trying to figure out how exactly where to put these big files, host them. So I have some ideas and I'm working on it.
With the units, was that kind of just ad hoc how you handle those, or did you apply some strategy?
These are well-known units in NMR, and it's just to make that unit conversion object, you have to pass it the dictionary of spectral parameters, and it reads from those and generates them, basically,
So it's like when you read it in a file, you get those.
Yeah, you get those, and I mean, I could probably make some different object that automatically generated them as soon as you read, but not all the file formats can actually give you, for sure, good units. Okay.
Thank you very much.
Proteins. So if we look in the protein data bank, which is just a big database of all the known structures, about 10% of them have been solved by NMR, and that accounts for about 8,000 structures. And that number has been growing over the years. So how does NMR work? First, we prepare a sample. We have to include isotopically labels. These are really small samples, so in the solution NMR, we're talking about less than a milliliter of solution in that little sample tube. Okay. All right, I guess I'll get started. So I'm JonathanJ.Helmus, and I'm working at the UConn Health Center, but a lot of this work was done at Ohio State University. And I'd just like to start my talk by thanking the organizers of this conference for inviting me and letting me present my work on NMR glue. So NMR glue is an open source Python module for working with NMR data. It kind of has a two-prong approach. It wants to tie together existing NMR software packages and also provide an environment for the rapid development of new processing methods and analysis routines and visualization. So in this talk, I'm going to give a little short background on NMR and protein NMR, discuss a little bit about why I wrote NMR glue and some of its design and features, give you some examples, and then since most of you are probably never going to run NMR, some opportunities for code. In the solid state, we pack them in tiny little rotors. We're talking about a few milligrams a sample. We put the sample in a large magnetic field. This is created by a superconducting electromagnetic, and they're quite large, very expensive instruments. We apply a series of very precisely timed radio frequency pulses, and then we collect the time domain's response to this. We have to do some kind of signal reuse that you might want to use from NMR glue. So nuclear magnetic resonance, or NMR spectroscopy, is an analytical technique that is used to characterize the structure and dynamics of chemicals. The most common use is for small organic molecules. This is the kind of NMR you might have seen if you took an organic chemistry class. But NMR can also be used to identify larger molecules such as proteins.